everybody. Nice to see so many people. So we have the pleasure to have Johannes Zeiher from Munich. So Johannes is professor at the LMU in Munich and also group leader at the Max Planck Institute for Quantum Optics. And there he is leading the efforts to build quantum computers with ultra-low gases and with single atoms, as he's going to tell us. So before that, Johannes was did his PhD in Munich, graduating in 2017, and then he went for 3 years at UC Berkeley, where he was doing cavity quantum electrodynamics. I don't know if you're going to talk a bit of cavities in your presentation. And now he is also having some activities that put together these few atoms in these quantum computing efforts, also with quantum networking objectives. So we're looking forward to your presentation. We're very happy that you came here. And so Johannes is still here this afternoon. In case some of you would like to book a bit of time, he still has, as far as I understand, a little bit of time at the end of the afternoon in case there's something urgent you'd like to do. Please.
Good. Great. Thanks a lot, Dr. Diep, and for the final introduction and also for the kind invitation having me. So I was here for the thesis committee, and I really enjoyed the visit so far. And it's of course also great to see so many of you here to listen to what I have to say on the work, as Jean-Philippe was saying, that we do in Munich at LMU. Hard to see. The point at LMU and at Max Planck Institute of Quantum Optics. So the topic of the talk is quantum computing, and in particular I want to place the focus on a specific way of doing quantum computation with atoms, which uses a specific type of qubit, metastable qubits, and I will explain to you what that is, and also try to convince you that that's actually quite promising approach to using the features we have in atoms to do quantum computing. So before I go into the details, let me start with a very general zoomed out view on the field of quantum computing, and I would say this is not only quantum computing but quantum technologies in general. So we are basically facing sort of a problem where, let's say, where we want to get to is this right corner up here at the top. We want to at some point get to some applications. We want to build quantum devices in general that can do some applications, and they have to be error corrected. What can applications be? As a scientist, I would say it could be a cool physics problem that you explore, quantum simulation, you try to understand something in detail that you have no way of understanding without such a device. And of course, as I said, this involves error correction, which itself has, you could say, is one application and has a lot of interesting physics. And in order to get actually into this corner here, you have to essentially bring together two things, which is on the one hand scaling the control in such systems, so this would be the vertical axis, and on the other hand scaling the size of the systems. What do I mean by that? Well, if I talk about scaling control, what I mean is to be able to do high-fidelity operations. We need to be able to control all the constituents. We have to be able to detect and read them out, for example. Scaling system size means I just need many of them, so I have to be able to build quite large qubit arrays. And then I think there's another quite important sort of diagonal thread where we sort of do both at the same time, in the sense that we develop new architectures that bring together from the start both of these aspects that enable high fidelity operations and large qubit arrays, and maybe get a shortcut more towards applications, or for example also error correction. And in the neutral atoms field in particular, along all of those dimensions, one could say there's been a tremendous amount of progress, actually just recently. I put a few references, this is an incomplete list, and you can see the earliest that I put basically is from 2023, and so there's like many results just coming out every year, in particular in the recent years. So let me actually be a bit concrete. So where does the field stand right now? Looking first at the size of the arrays that we can produce nowadays, you see on the left-hand side a picture, quite famous picture by now, which is from a group at Caltech from Manuel Endres, where they managed to actually trap more than 6,000 atoms in a quasar array. Yeah, that's great. Oh yeah, now you can see that a bit better. So if you squeeze your eyes a little bit, you see this is a quasar array that has more than 6,000 atoms trapped in individual quasars, and they also have a little zoom out where you can appreciate that. High fidelity operations, it's kind of similar. There have been many experiments, also very recent ones. So here's one example of a paper that came out, I think just 2 weeks ago, where people have shown that now you can do 2-qubit operations, 2-qubit gates, tangling gates. I will explain how those work, using Rydberg states with fidelities close to 99.9%, even slightly above if you accept that you do a little bit of post-selection. And then, and there are now many groups and many modalities in the sense of many different ways, different qubits, where similar fidelities have been reached. And then there's on the right-hand side here also this very nice work by the group of Michalukhin, where they've really come up with a new architecture. And this essentially involves putting together things that were known before, that is optimized to quantum error correction, where you define specific zones to do certain tasks, like a storage zone, an entangling zone, or a readout zone. And in the end, you make use of the fact that you can shuttle atoms, you can move them from one zone to the other, and then basically use the zone that is optimized for a specific task for building such quantum processes. And as I said, this has had a quite big impact because it's a natural fit to some error correction applications. And I will also explain a little bit how we can actually adapt that. So this is a general overview. The outline for my talk will be to essentially tell you how we in Munich, with our experiments that we did, can contribute to all of those 3 directions. So first of all, I want to tell you how we can use these metastable qubits for doing high fidelity operations. I want to tell you a little bit about how you can use metastable qubits and their properties to build new architectures, in particular building logical qubits. And then chapters 3 and 4, topic 3 and 4 are a bit more sort of on the scaling side. So how can we actually scale sizes of individual registers using optical lattices? And then time permitting, I want to tell you a little bit about the work that Jean-Philippe mentioned, where we are trying to put, at this point, smaller quasar arrays inside optical cavities to in the end realize quantum lattice. All right. Let me start basically with a brief overview of the workflow of the first part of the experiment. So how do we actually do the things that I will tell you about? So what we have is we have a so-called optical tweezer experiment, which I would say by now is more or less standard in the neutral atoms community. And there are a few key elements that you need. So what you need is you need essentially a high resolution objective, which has an NA of something that's typically higher than 0.5. In our case, it's 0.65. And we need devices, in our case, spatial light modulators and acousto-optic deflectors, to generate holographically spot arrays of individual laser traps. And this is sort of what you can see here schematically. So this is a small example of an array of tightly focused laser beams. What can we do with those laser beams? Well, we can overlap them with a reservoir of cold clouds, cold atoms, a magneto-optical trap, and we can load individual atoms inside these traps. And this is a typical image that we get after doing that. We get essentially these traps filled. We get them filled actually in the beginning stochastically. So you can see this is sort of a picture of a randomly loaded array where some traps are filled and some traps are not. And this is actually, one can show, it's really a stochastic process that happens. What we can do then is we can actually take an image like we do here and use the information of this image in combination with a second steerable laser beam that allows us to pick up individual atoms and then move them from one trap to the other and place them in predefined locations, and like that get to a picture that this is an example of where we just create what we call a deterministically filled array where each trap now contains exactly one atom at a known location. And this is sort of the starting point for many of the experiments we do. So in our case, I mean, this is sort of the technology of optical tweezers, and you can use different atomic species to put in those tweezers. In our case, what we do is we actually selected a specific species, which is strontium-88 to be specific, which is a bosonic isotope of strontium, because it's very well suited to what we wanted to do at the time when we started this experiment. It had basically a very good track record both in quantum simulation, but also in quantum metrology and quantum computing. And without going too much in detail, what makes strontium-88 special is that it's a 2-electron atom, which means you have 2 outer electrons and you compare them either in a singlet or in a triplet, and this gives rise to a very characteristic level structure where you see this singlet series where the outer electrons are, as I said, paired in the singlet, and this triplet series. And you can really think of those as pretty separate in the sense that you can do things in one series without significantly affecting the other series. As an example, what we do typically in order to get such images, for example, is we scatter photons off of the strontium atoms at a broad transition here at 461 nanometers that is coupling to singlet states and does not in the end involve the triplet states. We do, however, during taking an image also make use of the fact that you can couple in a controlled way from the singlet to the triplet manifold in order to do laser cooling, for example. And here what is quite nice about the fact that you have a singlet and a triplet series is that you have a very well-suited transition, so-called intercombination line, which is pretty weak, has a narrow line, and thus has very beneficial properties for laser cooling. And so this is one way in which we exploit sort of these features. There's more actually that you can do, that you can realize, which is that this intercombination transition, if you look at the selection rules, is actually a singly forbidden transition. So it's a spin forbidden transition because it goes from the singlet to the triplet. But there are also others that are doubly forbidden, like the one from 1s0 to 3p2 and the one from 1s0 to 3p0 and the one from 1s0 to 3p2. And these doubly forbidden transitions are also interesting, actually for various reasons. One is that they're used in atomic clocks. And second, given they are doubly forbidden, this means that these states up here, they're actually metastable because they cannot optically decay. And this actually gives rise sort of to a new perspective, which is actually to do physics from these metastable states and use really these metastable states as a resource. And this is one thing that, as I will show, is actually also quite useful for quantum computing because they have nice properties for that purpose. Before going into detail, in particular telling you how we can actually make a qubit out of those two states, I want to point out that strontium and also terbium, so these two electron atoms, have been studied quite a lot. For example, at GILA by Adam Kaufman and Jonier, in the case of terbium in Kyoto in the Takahashi group, and then in tweezer arrays also by Manuel Endres at Caltech and Jeff Thompson at Princeton. And so we have actually a lot of sort of very nice work that we can sort of leverage to do what we've been doing. All right, so let me now go and tell you a little bit more about these triplet states, in particular the metastable states, and how you can make qubits. And in particular how you can use this qubit, which we call the fine structure qubit, to do high fidelity operations. So again, before going into detail, let me take one step back and zoom out and tell you how can you make qubits in atoms in the first place. So what options do you have? And so in principle, I think that's an easy answer. You can make a qubit in any pair of atomic states that you can control, couple, and maybe that are coherent if you want to use the qubit for quantum information tasks. And so what you could do is you could, for example, use two different electronic orbitals and then to use one qubit state to be one orbital, the other qubit state to be the other orbital. And in fact, this optical transition from the 1s0 state to the 3p0 state or the 3p2 state that I showed you before in strontium, that also exists in a similar fashion in the terbium, is one example of such a qubit. Those qubits are special because they have very large splitting. You can drive them in a very simple way with a single laser. They're very weak transitions, so you need a lot of laser power. Typically they're also sensitive to temperature of the atom and also has a recoil associated with driving them, which might be problematic in some cases. Another very attractive route that actually has also been followed by quite some people recently is to not use two electronic orbitals, but use two nuclear spins in a single electronic orbital. And in this case, you just basically encode your qubit in the nucleus. This means that splittings are typically very small because you only very weakly couple to the environment, so you can apply a strong magnetic field and only weakly split the qubit. Drive this with two lasers in a Raman configuration, and that means that actually also insensitive to recoil and temperature. And given that the nuclear magnetic moment is much smaller than that of the electron, it's actually also very weakly perturbed externally by magnetic fields. So you can actually reach very long coherence times. And examples where you find such qubits are also the alkaline earth atoms, for example, in strontium-87 or terbium-170. And then there's this class here in the middle where you take two different states in the same electronic orbital. And an example of that would be hyperfine states in the alkali atoms. So this is what what you find in lithium, lithium too, but also in rubidium and cesium. And here qubit splittings are typically gigahertz. You can also use Raman lasers to drive this. And similar to the nuclear qubit, they're not very sensitive to recoil and temperature, but they're usually more sensitive to external perturbations. Now, the fine structure qubit that I will be talking about is sort of part of this middle column here, where things are similar but still slightly different compared to the alkali qubits. Namely that for these fine structure states, the splitting is not in the gigahertz range, which is typical for alkali atoms, but it's rather in the terahertz range, so it's much larger, and I will tell you why that is actually an advantage in some way. But otherwise, things are still comparable. You can drive this with 2 Raman lasers, and because of that, this is also rather insensitive to recoil and temperature. And you find such qubits in strontium-88 or also terbium-170. So this is essentially what our level scheme looks like. So as I said, we work with these 2 metastable states, and I want to show you now how we can basically essentially reach all the points or achieve all the elements that we need to use that qubit for quantum computation. And in particular, what I'll show you is how we can do single qubit operations by off-resonant Raman. So we start in the 3.0 and we go via an intermediate state to 3.2. I'll show you that we can actually keep these states coherent. I'll show you how we can do 2 qubit gates, and I'll also show you how we can shuttle around the qubit. Before doing that, I actually want to point out that there was a lot of nice work actually done on this qubit, basically in parallel as we started also doing this in the group of Florian Meinert and Tilman Pfau in Stuttgart, and also in the group of Sebastian Blatt in Munich. And so we could also leverage a bit of the knowledge there. So let me start showing you our single qubit manipulations. What we do here is we essentially initialize the system, strontium, in this metastable states, and then we drive this off-resonant 2-photon transition, and this will become relevant later. We use 2 photons at 679 and 707 nanometers. So they are relatively far apart in wavelength. And what we see then, if we do that and we detect essentially the population in the 3.0 state by pumping this down and then detecting here, is we see these Rabi oscillations, and you can see they're actually quite nice, quite coherent. So we can drive many coherent oscillations despite the fact that these wavelengths are so different. So that means, first of all, that we can actually build these laser systems that are relatively phase coherent to another, and also relatively phase coherent to the qubit itself. Not only can we drive Rabi oscillations, we can also do gates. So we can basically just apply pulses, and we can draw sort of these pulses from a Clifford set, Clifford gates composing these from pulses. And if we do randomized benchmarking, at the moment we get up to something like 99.6% for Clifford fidelities, which is lower than we think it could be, just because we are a bit limited still by phase noise on these 2 lasers. And we are actually working on an upgraded laser system to fix this. If you do the calculation, it should be easy to get actually way beyond 99.9%. The second point that I promised to show you is that not only can we drive the qubit, but we can also make this qubit coherent. And the way we benchmark this is by doing different kinds of measurements to benchmark the coherence, namely, first of all, a Ramsey measurement, where we just do a pi/2 pulse on the qubit, bring the 2 qubit states in a superposition, then hold it for a variable time, close the interferometer with a second pi/2 pulse, and then measure the Ramsey fringe contrast as a function of dark time. And we see basically here that after about 500 microseconds, the contrast has decayed to 1/e time. Luckily, we understood at the time when we did this that this is mostly due to inhomogeneous broadening, because we are slightly sensitive to the different tweezer depths here. And that meant that we could actually remedy this problem just adding a single spin echo, which removes the inhomogeneous broadening. And doing that, we actually see already a significant boost here of the coherence times by almost 3 orders of magnitude to something like 36 milliseconds. And then we can go on and do a bit more complicated dynamic decoupling using XY4 sequences, and by that get up to something like 100 milliseconds. And because most of the effects that the qubit here is sensitive to are actually because of the depth of the tweezer, so they're actually due to the tweezer itself, and because of the light in the tweezer. Yeah, this has some coupling to the qubit states, effectively via effective magnetic fields and fluctuations. We can actually also remedy some of the decoherence by just going to more shallow tweezers, while still being able to work with the qubit. And like that, we can actually get to coherence times of something like 3 or 4 milliseconds at the moment. And this is actually much longer than the time it takes us to make a single gate. So we were actually quite happy about such long coherence times. Maybe one detail that I don't want to spend more time on is we can actually also get an idea of what's the atom-atom coherence. So what we measure here with these sequences is actually the atom-light coherence. From a slightly different measurement, we get the atom-atom coherence, and we think that this is actually longer, like close to a second or something like that. So we think that if we can improve on the stability of our lasers, we could make this qubit even more coherent. But already the 350 milliseconds that we measured here are more than enough for what we want. So this checks basically the two first points. We can do nice single qubit gates and also measure long coherence times. And so one could say that makes that qubit a promising candidate, at least, to start doing experiments. Now what I want to explain is how we can get beyond a single qubit and do 2 qubit operations, in particular coupling to Rydberg states. So how do we do that in general? Well, the idea now is that we actually expand sort of the level scheme that we use from the 2 qubit states and include a highly excited state in the atom. So this is the so-called Rydberg state. A Rydberg state, really think of this as a state that is just below the ionization threshold of the atom, and that means it's very easy to polarize it actually. It has a very strong DC and also DC polarizability and very sensitive to electric fields. As a consequence, you also have very strong van der Waals interactions if you have 2 Rydberg atoms. Because you can essentially think of one, if you have a Rydberg atom there and a second one here, that the electric field generated by this electron will actually sort of perturb the other one and vice versa, and this is exactly the mechanism that gives rise to van der Waals interactions. So if you draw basically the interaction energy between 2 Rydberg states as a function of distance, then you see that if you have two atoms in these Rydberg states, you have this extremely large repulsion for distances that are quite characteristic for our system. So I didn't mention this explicitly, but when we have these tweezer rays, the separation between the atoms is on the micron scale. And you can see here really sizable tens of megahertz or even like up to hundreds of megahertz of interaction energies at these characteristic distances. What is the consequence? Well, if we start with 2 atoms in the 3p0 state and we take a laser and try to excite them to the Rydberg state, then if the distance is large, which is what's shown here, that's no problem. We can just do that and we can independently drive those atoms. However, if we try to do that at small distance, where you have a very strong Rydberg-Rydberg interaction, you will see that you can only ever drive one of the 2 atoms in the Rydberg states, and then the second photon will be blocked from exciting the second atom because essentially this doubly excited state is just shifted out of resonance due to the interactions. And this comes with a phenomenon, causes a phenomenon called Rydberg blockade, which is exactly this idea that within a certain range, which you can get roughly by equating the interaction energy with a drive Rabi frequency, which gives rise to radius. So within that radius, you can only excite one atom to a Rydberg state. And that actually also, if you think about it, if you drive, for example, such an ensemble, means that because you don't know exactly which of the atoms you drive, you sort of have a symmetric superposition of all of those possibilities. You can actually now, in the case of 2, realize this W state, which for 2 atoms is actually a Bell state. So that's nice. So you see, you can actually use this strong interaction to get entanglement, but it's not entanglement we want. So if we want to do a 2-qubit gate, we want the entanglement basically between 2 qubits. So we want essentially entanglement between 2 atoms that are only sort of living in these 2 qubit states. Well, now what we generate, what I showed you here, is an entangled state between 2 atoms where, if you want, the qubit is encoded between the ground and the Rydberg state. So we need a way to transfer the entanglement from the ground to Rydberg basis to this qubit basis. And luckily, this is something that by now is pretty standard. So we can exploit the Rydberg blockade so exactly this idea that you have an entangled state up there if you have 2 atoms with a Rydberg blockade. to actually realize entanglement between two qubits encoded in these ground states, or in this case in the metastable states. And what we need to do is actually a so-called time optimal gate. Time optimal in this case means that we have to run a pulse here that has an intensity variation that is close to a square pulse, and in addition we have to actually modulate the phase of the laser we use to drive these two atoms. And we can actually drive both at the same time with the same pulse if we do the correct phase modulation. And then it turns out that if you go through this, you can see that if you have both atoms here in the zero state initially, and you drive the system with this phase modulation to the W state and back, then because of the different coupling of the ground state to the W states, compared to all the other combinations you can have here, so you could have one of the atoms in this state and one in this state, which would be the 0-1 state, or you could have both in the zero state. And due to the difference in coupling here, the square root 2 compared to the case where you have only one of the atoms in the one state where you don't get the square root 2, you can actually transfer the entanglement from this W state effectively into the entanglement between the qubit states. So really you can think of this as taking different trajectories, optimized trajectories through these Bloch spheres in order to actually basically bring this entanglement from the Rydberg to ground, the Rydberg basis to the qubit basis. And if you do things right, the upshot here is that this pulse with the phase modulation actually realizes a controlled Z gate up to single qubit phases, which you can correct. And by now, this is sort of the gold standard. So most of the results that came out recently were using exactly such a modulation or similar modulation to achieve these high-fidelity gates. All right, so that's the theory. So we can actually program these pulses, and we can also program the phases and hope that we do a controlled Z gate. But how does the experiment look? So the way we benchmark what we do here is by a randomized benchmarking. So we initialize the two atoms into one state, so in this 3p0 state here. And then we run a sequence where we have a unitary that we drive on the system that actually contains single and 2-qubit gates. Then we have a variable number of these controlled Z gates and a random unitary, a random single qubit gate in addition. And then we do, in order to compensate the number of single qubit operations, sort of in every sequence, a variable number of single qubit operations, such that taking these two blocks together, the number of single qubit operations is always constant. And the only thing that varies is the number of controlled Z operations. And of course, what you can do then is you can basically benchmark the performance of the system as a function of number of controlled Z gates. And what we look at here is we look at the probability of finding the system after doing this whole operation again in the state that we started from. And this sequence here is designed in a way that if everything is perfect, we would actually perfectly get back into the starting state. So you would actually expect, without errors, to have a unit overlap up to spam errors here. And so this is how you should understand this graph. So we have here on the y-axis the return probability, so the probability to find the state in the initially prepared one as a function of number of controlled Z gates. And you can see essentially this drop here, and this drop only depends now on the number of controlled Z gates, which means that if you make sort of after 10 gates sort of an error, you can essentially divide the number of gates out and get the error per gate from such a sequence. And if we do that, what we obtain is we get a fidelity for these 2-qubit gates that is 99.86%, so actually close to 99.9%, and this is something that we recently put on the archive. There's a small disclaimer here, which is that because of the way we couple to the Rydberg state, we actually have some loss. We couple from this 3p0 state at the moment. And while we do that, we actually ionize the 3p2 state. So that's an imperfection that we understand very well, and we also understand that the consequence very well. So in order to get actually this gate fidelity here, we have to post-select on the loss. What we will do, and we have the laser for that essentially on the table already, is we'll fix that loss just starting from the 3p2 state and do the exact same gate starting from 3p2, and then this curve that has no loss correction and the one that has loss correction should actually essentially coincide. And so this is something that we're preparing right now. But you already see that the physics of this gate of Rydberg blockade actually works very well for strontium, and this is already a very good starting point to do further experiments. All right, so that checks the 2 qubit gates. Let me come to the last point, namely the shuttling of qubits. So as I said in the intro, there's this very nice new architecture that relies on different zones, functional zones for neutral atom quantum processes, where you take atoms and you move them coherently between those zones to do operations on them. And of course, prerequisite for that is that you can actually coherently shuttle these atoms. And so that's something that we also tried out for the fine structure qubit. And the way we characterize that is again via Ramsey contrast, and we just essentially take an atom, move it, do a pi pulse, move it back, and then we essentially measure the Ramsey contrast as a function of the number of these moves, including this little echo. And we see that looking at how this contrast decays, we can do about 80 moves before again reaching the 1/E Ramsey contrast. So you can actually keep the atom coherent while moving it around for quite a long time. And that's of course also quite nice, because that means that we can unlock this architectural feature that we have a zone-based quantum computing system. All right, so also this last point is checked. And before I proceed, there are actually 2 small details that I don't want to go into depth about, which are 2 additional features that you get from the metastable states. The first one, and I would say there are actually nice benefits. The first one is actually very generally true for metastable qubits, which is that if you make errors, so for example, you drive a single qubit operation, then there's actually a chance that the error does not lead to a Pauli error, which means you, for example, get a spin flip or a phase error in the qubit, but there's a chance that the error just leads to decay into this dump state down here, into the ground state. And then you can actually go and take an image, and so you get additional information on the error. You know that it happened, and you know where it happened. And this is what's called an erasure error, and you can do what's called erasure conversion, convert errors into erasure errors. And that was figured out by Jeff Thompson a few years back. Actually enhances and improves quantum error correction, actually in a quite beneficial way. The second nice feature about this metastable qubit, and this we've implicitly actually used already, is that in strontium in particular, there's this repump transition in the green, which allows you to selectively depump this 3p2 state without populating the CP0 state right back into the ground state. So you essentially can transfer these atoms into the ground state without, almost without populating 3p0, and that allows for a spin selective readout, because you can do, after every shot, you can first transfer 3p2, take an image, and then transfer 3p0, take an image. And that actually allows you, for example, to post-select from loss, which is what I showed you we did for these high-fidelity gates. And it's also a very nice feature, which also is actually quite useful for error correction, if you have information on whether an atom, this ancilla for error correction, has been lost. All right. Taking all of this together, I now want to proceed and show you how we can actually build an interesting architecture for quantum computing, in particular quantum error correction, based on these fine structure qubit states. And before I go into the details there, let me zoom out and motivate quantum error correction. And I already said this in the beginning, that if you want to do, let's say, applications, it's pretty clear by now that our native gates and operations are probably going to be too bad, and we need to be able to actually error correct systems. And so future scaled quantum computer will most likely and most definitely actually require quantum error correction. So in a nutshell, what is quantum error correction? And this is of course very short and also directed towards what I'm going to tell you. But the way I think about quantum error correction is that you take effectively the information, quantum information you have stored in a single qubit, and physical qubit in this case, and you essentially distribute that over many physical qubits, keeping sort of a limited number of qubits as the informational content. So for example, to make it very concrete, you can just take this one qubit and store this physical qubit and store this in d squared physical qubits. So you still have one qubit degree of freedom, but d squared physical qubits that you use to decode this. Why do you do that? Well, you introduce this overhead in order to introduce additional checks, and those are the so-called stabilizer checks. So there's some built-in redundancy which allows you to actually measure whether the qubit is intact or not without destroying the logical information. This is this redundancy. And then there's a third very important thing, which is that, of course, this requires some work, right? You have to do operations. And in the end, what you need to get to is you need to get to a situation where those operations pay off, in the sense that the more operations actually make in the end the logical information better, despite having more operations. So you have to be above a certain threshold, and you have to be able to outperform the physical counterparts if you by going through that pain of making things redundant. And I think those are, in a nutshell, three of the most important facts about error correction. And what I think is also very important is that we think about these things now, because if you do it, you will actually realize that these logical qubits many times work very differently from their physical counterparts. If you think about algorithms, you have to really change the way you think about how you can run algorithms. So I think it's very important to actually go through simple test cases and toy models for error correction. All right. What I think is also very nice, and this is a general statement about sort of the field of quantum technologies, is that we now have actually several experimental platforms that are at or near the threshold where this error correction pays off. Just to give you 3 examples, if there was this very nice result from Google 2025 published, where they show that if you have a certain error rate, that you can, by changing the overhead, which is encoded in this little d, this distance, you can actually improve sort of the logical error given a certain physical error, as long as the physical error is better than a certain threshold. So here, this is really a proof in a sense that you can do better with a logical qubit, with a single one here, than with a physical qubit. Similar results were obtained in the neutral atoms in the Looking group recently. So you go from a distance 3 to a distance 5 code, which is essentially quantifying the overhead, and you see things get better in the sense that the logical error gets better. And very recently there was also a paper from Continuum where they showed that if you go from one code to another code, which in this case also increases the overhead, you can also reduce the errors that you make. So this is also sort of in the same spirit. And I think that's super cool, because it really shows that this is not just fantasy, but we can really get to a point where such systems can be built. And there's an important consequence, which I didn't actually say, but in principle, if you could now scale the number of physical qubits further, so you could increase the distance to 9, 11, and so on, the error should plunge down. Yeah? And so it's very important to actually be below the threshold where this behavior occurs. And that's why these experiments are so important, to show that you can get below the threshold. And now, in the end, it's just making larger systems. And in principle, this error should drop. So that's why this is so exciting. Cool. So what can we do in this direction? Well, we can use our Strontium platform and actually also try to realize a logical qubit. And in particular, what we tried here is to realize a so-called 4-2-2 code, which means that we have 4 physical qubits, 2 logical qubits, and a distance, so redundancy, of 2, which actually means it's not an error correction code, it's an error detection code, so we can actually not correct an error, but detect one, but on 2 logical qubits. And we do 3 things. The first thing is we actually do this redundant encoding. So we take a single physical piece of qubit information, and we store this in logical qubits. And in particular, in this 4-2-2 code, what we need to do is we need to generate sort of these basis states of 2 qubits. And you can see for the 4-2-2 code, those are essentially Bell states, or a combination of Bell states. And we do that in order to get this additional information, these stabilizers that are redundant checks that we can run in these qubits, which we can use in the end to correct, in this case actually to detect errors. And in different codes you can use them to correct errors. And so what I'm showing you here is that we can actually target a specific one of those, and with a physical circuit that looks like this, we can actually realize exactly such a logical state, which would be one logical qubit in state 0, the other one in state 1. And we can do that actually with quite a decent fidelity. What we can also do is we can actually go one step further. We can realize such a logical qubit, and then we can actually use this redundant information. We can read it out on the logical qubit, actually without destroying the logical information. And that we do via another atom, a so-called ancilla atom, that we use to actually measure this 4-body operator here. So we do that by moving it past the logical qubit and then reading it out in addition. And doing that, you can actually see that we can improve the logical information that we obtain if we do the check compared to if we don't do the check. So this additional information actually helps us to make the logical qubit better than if we didn't do the additional check. So that's also a very important requirement for quantum error correction. And then the third thing that we did is we actually wanted to show that you can also realize logical entanglement, in particular to make a logical Bell state. And in this case, I'll show we can actually slightly outperform what we can do at the physical level. Again, we can realize such a logical Bell state with a physical circuit. So these are the 4 qubits in the 4-to-2 code. And then what you see is if we look at the fidelity of our logical state, this is about 99%. It's better than what we can do in a raw setting, which actually is not surprising, because what we do in order to get from raw to logical is we use stabilizer information, which means we post-select. Yeah, so the fact that this is higher, the blue bar is higher than the gray bar is maybe not surprising. But what we should do is we should compare the blue bar here with the best possible 2-qubit physical Bell state that we can do. And this is essentially something that we did before that, and it's roughly similar to what we get to here. But we actually realized these Bell states, including all post-selections we can do before, with a fidelity of about 98 or something, 0.3%. And you can see that now this logical state is slightly better than the best physical one that we can do. So in this aspect, not in all aspects, which is what we need for error correction, but in this aspect we can actually do something better using logical qubits than physical qubits. And so this is of course the first step towards that scaling machine. It's again not at the level where we can say everything gets better, which is what you need, but it's a first step and it's one task where this pays off. And so I think that sort of lays the path for the future. Now, one thing that I didn't show you, and I won't have so much time to go into detail, is the technical tricks we actually used in order to get to this. So, maybe to go one step back, if you look at this, in some of these circuits here, you actually need local operations. Yeah? And I didn't tell you how we do the local operations. And this is actually something that is very nice about the fine structure qubit, which is that these photons that you use to drive the 2 fine structure states, they actually have quite different frequencies, different wavelengths. And what that means is if you drive an atom with those 2 photons, then depending on where you place the atom will actually see a different phase, difference phase between those 2 photons, which is what's relevant in order to drive this 2-photon transition. And what that means effectively is that depending on where you place the atom relative to this wave, this running wave, you can actually change the axis about which you rotate the atomic state. So you make either a rotation about the x-axis of the block, so the y-axis, or anything in between, depending on where you place the atom. So you have a way here of doing local operations by placement of the atom. So that's something that we use here. And the second thing that we used is we actually also realize mid-circuit operations here, which you need, for example, to do these stabilizer checks frequently. You need to measure the stabilizers all the time by actually addressing atoms in motion. So the idea is that an atom, if you try to address it with a photon, it actually sees a Doppler shift. And in particular on these narrow line transitions, this Doppler shift can be so large that it's actually easy to resolve the velocity of an atom spectroscopically. So in other words, if an atom moves at a certain velocity, the transition is shifted, it's shifted to a different location than when it moves at a different velocity. And so this you can really easily resolve, and we can actually even drive Rabi oscillations on moving atoms if we just set the laser to the correct detuning. And you can see essentially the coherence here is almost not affected. And this provides you with, first of all, a way to do mid-circuit operations. You can just move the atom at a certain velocity and then only talk to the atom that you're moving. And second, this is really, if you think about it more generally, like a new dimension for quantum computing. So it's really a new degree of freedom that, if you want, extends your 2D space into a 3D space. So if you do 3D, think about a 3D space and you have 3 velocities, you can even do operations in the end in 6 dimensions. And I think that's a very nice sort of route forward to actually make some of the operations more efficient. So what can we do without going too much into detail? I think a very nice fit for this architecture is measurement-based quantum computing, where you need to actually exactly do the things that I just told you about. We actually need to do some mid-circuit measurements that are qubit specific. We need to be able to do parallel entanglement generation. For measurement-based quantum computing, you need to generate a resource state, a so-called cluster state. And then you sort of need to run this in a circuit, so you need to be able to initialize specific atoms again and again and again, and this you can do with velocity-selective initialization. And we tried some of the features here. For example, what we did is we realized such a cluster state, such a resource state with a specific circuit that you see here, where a lot of these operations run in parallel. and we can actually get quite good fidelities on this cluster state. I have no time to go into detail, but we can check essentially all the stabilizers of the cluster state, and we see they're all well above 0.5, which is the threshold for entanglement, actually genuine multi-particle entanglement of this cluster state. So we already went and showed one of the components of this scheme. And just to give you an idea of what this looks like then, if we put everything together, you really see like these atoms moving around. And this then, okay, this was the initialization step, now we make the cluster state, this was the measurement, and then you essentially repeat all of this. And so you could really keep the system going like this, and for example, also build larger cluster states. And I think that's an exciting way forward for the platform. All right, very briefly, I don't think I have so much time, maybe a few minutes. Okay, perfect. Very briefly, I want to show you how we can scale this, so this I can be really brief with, because essentially what we do here is we have our tweezer array, and that I showed you before, and what we can do is we can now overimpose a lattice, which is built in a way that we can actually load atoms directly in there from our magneto-optical trap. And you see here a picture of about 10 or 12,000 atoms that we load directly, like we would load a tweezer array, but at a very different scale. And what's important is two things. First, we can load directly from the mod, and second, we can still identify single atoms. And we can actually do more, so we can also do continuous operation of such a machine, of such an experiment. So we can essentially take the many sites we have in this optical lattice and assign some of this as a loading zone and the other one as a storage zone, and we continuously load the loading zone, move atoms to the storage zone, which is basically where we keep them in the end as a register, as a storage register, and we can sort of do this continuously with some tricks and keep this alive for over an hour if we want to. And of course now a very nice feature would be to put the velocity-selective quantum computing that I showed you before together basically with this continuous loading. All right. So, and I think that's a very, very nice scaling prospect that we've explored in a separate stream, but that would be very nice to put together, and I think there's actually no big roadblocks to try and do that. Okay, very briefly, towards the end, I want to use a few minutes to also advertise this new project where we actually now started to combine these quantum computing systems with optical cavities. And the idea here is actually that at some point your single QPU node will be limited in size, right? You can scale in a lattice maybe to 10,000, maybe 100,000, maybe even more qubits, but at some point you want to go to larger sizes, and you need to think about interconnects. So you need to start linking different QPUs. And one thing that you need, of course, is you need the QPUs themselves, you need the interconnects, but in particular you also need the interfaces here. So you need to be able to talk between these QPUs. And the experiment that I want to show you now is one where we build such an interface, and this interface is actually composed of such a QPU that is coupled to a cavity, strongly coupled to a cavity, and the QPU, of course, has all the features I showed you before. So it has these Rydberg gates, it has individual atoms that you can control, that you can move around, and the additional feature is this cavity coupling. And this is something that is actually not super straightforward. There are a few groups working in a similar direction, like Temple, Dan, Stanford Kern, Bladan, and I guess it's of course also related to what's going on here, to have microscopic access to atoms inside optical resonators. And what's the challenge in particular for the Rydberg states is actually that these cavity mirrors will actually generate electric fields. And the Rydberg states are extremely sensitive to electric fields. And this is why we sort of thought from the beginning of how to actually mitigate problems that come from the electric fields emanating from the cavity that would modify the Rydberg states and make your quantum operations worse. So what's the status of the system? Well, at the moment we can realize qubit arrays of rubidium in this case. So this is to make our lives a bit simpler. We use rubidium to start with. So we can make qubit arrays of about 50 qubits. We can drive them, in this case, between two hyperfine states very coherently. So we can actually do single qubit operations if you want. We've also done randomized benchmarking. We get quite nice coherence times. So the single qubit sort of toolbox, I would say, is pretty much in place. We can also actually couple the system to the cavity, and so here you see how this works. We have the array inside this near-concentric optical resonator, and the way we check the coupling to the cavity is in the dispersive regime. We basically see the dispersive cavity shift due to the presence or absence of the atom, or due to the presence of the atoms in this case. So you see an empty cavity resonance that is modified by a dispersive shift proportional to the number of atoms coupled and g squared over delta. That signifies actually strong coupling. And if we work out the cooperativity here, then we estimate that for this cavity, which has a few problems, it's slightly misaligned, the cooperativity is about 0.5 in this specific case, but we didn't actually pay attention to how the atoms are aligned, and the cavity mode is also actually a bit smaller than the array here, so we think the single atom cooperativity would actually be closer to something like 1.5 or so if we take those factors into account. So we are in the reasonably strong coupling regime. The second thing is the addition of Rydberg states, and this is something that we've been working on. And as I said, there's this problem with electric fields that you have to think about. So the atoms sit here, the cavity mirrors are about a centimeter away. And what we did is we actually did a Rydberg spectroscopy starting from the ground state and going to the 53S state. And we see that as we drive the cavity piezos, the Rydberg line only moderately shifts by a few hundred kilohertz, in this case about 400 kilohertz. And this is actually well manageable. This is not a lot. And the reason why it's so small is because we actually shield these piezos by sinking them inside our cavity mount. And what we obtain here, this shift, is actually pretty close to the prediction that we have when we do sort of a finite element calculation of the mount and calculate the electric field that we expect at the location of the atoms. And you can actually see, without going into detail, that the field is suppressed by almost 2 orders of magnitude, which actually leads to a resonance shift suppression of almost 4 orders of magnitude here. So in other words, if we hadn't done this carefully, then this line, like the shift here would not be 400 kilohertz, it would be more like 400 megahertz, and then of course you could not do any of these experiments. So it shows basically that this shielding is very important, and also that you can do it, and that you have this control. And so the last thing that I want to briefly show you is that we can also do something interesting with the Rydberg atoms. So we can actually prepare these little ensembles within the Rydberg blockade that I described before. And we can drive them, and what you see here is you see basically post-selected data where we post-select on the initially prepared ensembles in such Rydberg blockade. So we post-select in the end, did we prepare 1, 2, 3, or 4 atoms, and you can see that the dynamics depends in this way as a square root of n actually. If we plot the Rabi oscillation, Rabi frequency as a number of atoms, depends as a square root of n here. And this is actually exactly consistent with realizing this W state that I described, which means we can actually realize this entangled W state, where the entanglement in this case still lives between the ground and the Rydberg state inside our cavity despite the presence of the cavity. So this is kind of the essential step to now make gates and also in this system, and that's something that we're working on. What we're also working on, we are working on basically putting all the tools together, and very recently, just last week, we actually managed to resort our atoms, and we can now make little ensembles. So this is inside the cavity, so the cavity mode is basically aligned with the long length of this array here, and we can now make these small ensembles here, just basically moving the atoms around. So these are 2 images of the same cloud, which, okay, I guess you have to believe me, and you can see this is before, and this is after resorting, and you see there's still some work to do, but we can already make this, and at the moment then now, on top of that, we'll now basically start doing Rydberg gates and really put this toolbox together. I think this is a platform that has many applications. I will not go into detail, but we are interested in sort of making logical qubits and really thinking about remote connections between logical qubits. We can also, I think, do very nice photonic state engineering, and I think that's also interesting perspectives for quantum simulation, actually, this platform. If any questions on this, feel free to come up to me, and I'd be happy to talk through any of these ideas. The most important slide brings me actually close to the end. I should thank the team. So this is the strontium team that was pushing very hard on all of the results in the strontium experiment on these metastable qubits. And of course also a big shout out to the cavity team that put together this cavity platform and is now very motivated in moving this further, improving all the bits and pieces, and then really putting this also to use for nice science in the future. And one last slide, we actually also have a startup in Munich. If you're interested in neutral atom quantum computing on the sort of more commercial side, there's Planck. If you have any questions on that, feel free to reach out. I'd also be happy to talk about that. And this is the very last slide, the summary. I hope I could convince you that these atom arrays are very interesting for various things, quantum computing, also quantum networking, and there's also very rich physics in there. And I'll leave up the summary, and I'd be happy to take your questions, and thank you for your attention.
Thanks a lot for this very nice overview. Questions?
Yeah, very nice. So regarding the cavity you are building now, how is it supposed to work? Because you said it's for this quantum internet, so to connect different nodes. But the cavity will talk to like the entire array, you know? So how is it supposed to work in the end?
Very good. So you need some sort of local control it's not well defined, let's say, because I think there are many different options. But you're very right, you need some sort of local control. I think the way such a network will work in the end is that you have individual atoms coupled to this cavity, and you essentially produce Bell states. And you do that by doing that in two systems at the same time. And then you do a joint measurement of the photon, and that projects the two atoms in the Bell state.
But you need for just one atom at a time, not...
Exactly, you do it for one atom at a time, but then you have to do that all the time to basically saturate the rate at which you can do it from the cavity, which is essentially the kappa, roughly. What that means is you have to basically always make sure that when you can try again, you have either the atom that you had before in the cavity that's ready to do it, or you bring in a new one. Yeah? And so then you essentially have to set up some pipeline where you do that all the time. So you can think about moving atoms through, or you address an atom like all the time, coupling it in a controlled way.
So the mode of the cavity is smaller than the spacing between the atoms?
Yes, so this is one way to do it. Either you do it like that, you have one atom inside and then a bunch outside, and you set up a stream, and then whenever you have the atom inside, you do the operation. Or you can also do local addressing inside the cavity, coupling it sort of with an additional laser beam to the cavity, which we also have ideas on. It's actually very similar to what Jean-Philippe is doing. You essentially shift the excited state, and like that you can actually couple, you can turn on and off the coupling.
Yeah.
Thank you.
More questions?
Thanks for the talk. I'm not sure I understood how does putting the atoms in the cavity allow it to communicate with another QPU?
Okay, so this is, of course I didn't say much about this. I have a slide that I didn't show that shows that. So what's the idea? In order to set up remote, have two QPUs connected, you need to set up some remote entanglement between the two. Right? So you need some process that entangles one QPU with another QPU. And you can use that entanglement as a resource in both QPUs. And like that, of course, you can essentially connect the two. And how does that work? Is essentially what I was describing. So you have one emitter in each cavity. So this is one way of doing it. You have one emitter in each cavity, and you emit photons into the cavity, and then you send those photons to a joint Bell state measurement if they're indistinguishable, because the emission of the photon, the atom and the photon after the emission of the photon are entangled, and this happens on both sides. You do a joint Bell state measurement of the photon, you will actually project the system into a Bell state between the atoms.
But when you perform this measurement, the information is being shared classically by a classical computer?
You do have to yes, you have some classical information, yes, that flows. So you can do it in a way that you need that classical information. Yes. So you select a specific Bell state that you measure, and then you have to make use of the fact that you've obtained that Bell state to say that your atoms are in the correct Bell state. That's a classical piece of information.
More questions?
Okay. So these non-local gates for the shuttling look very good. I was curious about timescales though. Like the video you showed basically is that real time, or how long does it take to do one of these non-local?
It's not real time, so of course that's a good point. Which is, I would say, general discussion in the community. So shuttling always takes time. Yeah. So if you look at the time budget, then a gate takes a few hundred nanoseconds, and the shuttling sequence or shuttling move takes almost 100 to 1,000 times longer, so 100 microseconds roughly. I think if you only do a few of those operations, and you look just at the time budget, it will always be better to do just with back gate. But the big point about the shuttling is that you can do this highly parallel. Right? You can move all the atoms in principle at the same time if you have a powerful enough modulator. And then the question is, can you leverage that parallelism? And it turns out that for logical qubits, which is essentially a group of atoms that in a large amount of time do the same thing, you actually can profit a lot from this parallelism. And this is why I think at the physical level, maybe it would be better to just do standard swaps. But if you go to larger groups of atoms, you can leverage the parallelism, and then this can actually play off. But I think this is a discussion that's ongoing. So one has to look, let's say, at an architectural level to make a statement. One thing that I can say is that this velocity selectivity that we have actually can reduce some of the shuttling, because if you one way of using this is you make an operation in a certain zone, and then conventionally what you would do is you would basically move the atom far away to another zone. Now what we can do is we can actually just accelerate the atoms a little bit, and then bring them to a different state, and then sort of do those operations in place rather than moving to another zone. So the bottom line is, I think there are many savings if you use atomic physics in maybe a clever way or some way that is maybe unconventional, and so I think there's still a lot to be discovered.
More questions? Yes?
Maybe a stupid question. Is there a specific reason why all the lattices that you showed, they are always like rectangular, square lattice? Would it be interesting to think about something else, like triangular? Or
for the tweezers, you're not constrained. You can do anything in principle. For the shuttling, it's convenient to have square lattices because the way we generate that is with AODs, and you can in principle do non-square configurations. It's a bit more effort. So I don't think it's excluded. So I think what people are working on also is, of course, to get rid of AODs and use other ways of shuttling where you have really completely arbitrary configurability. I think that's also something that we'll see.
I have another question.
So one question here, then
Indeed, first.
It's just a question, like, why do regular people who do like optical tweezers, they don't want to use optical lattices? Because then that would be a really easy way to just scale up your platform.
Yes. I think optical lattices are indeed very nice for scaling up, and I think if you really think about 100,000 or 1 million qubits, and you say, okay, maybe interconnects are too hard, then I think they're probably the way. But I think it requires, to use them, requires more co-design, because you lose, of course, some flexibility you have with the tweezers. And that means you have to sort of think about what code, error correction code, for example, you want to put in your system. And then you can actually adapt the error correction code to make it compatible with the lattice. And I think that's a very interesting and exciting direction, but it's something that requires a bit more commitment. So if you don't want to do that, you just do tweezers, because then effectively you can do everything.
But another reason is that you don't want the atoms to be so close to each other, right? Like in optical tweezer arrays, you can put them very near.
But I don't think this is, so for the lattice, I would say this is a feature rather than a bug, because you have those sites, but you don't have to use them. So we actually have resorted arrays in the lattice where the atoms are at a 2 or 3 micron distance. That's no problem, actually. So I think that is no concern that I would have.
Okay, and if they are too close together, they tunnel, right?
Well, you make the lattice very deep, so there will be practically no tunneling. But so I think that's something where I would say I'm not concerned about. I think at the moment it's more convenient to use tweezers just because you have more flexibility and you can try out more things. But you can also limit and then scale, and I think that the lattice is actually the best way.
Yeah, can you control the symmetry of the lattice, or it's formed by closing packing? I mean, if you want, you can change the symmetry and form a new architecture.
Yeah, that's also a very good point. So first you can play with the lattice geometry. We do a square lattice here because it's stable and it's easy. But I mean, we know from the cold gases physics and the cold gas community in general how to make more complicated lattices, and also how to make it stable, and which lattices are stable and which are more challenging. And yes, one can also do. I think for us it was convenient to do the square lattice in this case. But I think it's a very interesting idea.
Okay, one question.